Hello and welcome to Physics for Play. In this video, we're going to spend some time looking at sample systems that behave simple harmonic motion, and we're going to spend some time visualizing them. Let's get started. So our goal for today is to walk through a few sample systems that can be described by simple harmonic motion. So we began our discussion with the simple harmonic oscillator by saying that we're going to define it as anything that undergoes an oscillatory motion, or the way I put it was anything that goes boingy, boingy, boingy. And we're going to keep that definition, and we're going to explore a few different examples of systems that you can describe that way. As a reminder, these systems, mathematically speaking, can be described as anything that has a restoring force that goes as minus a constant times the displacement. Or if we're talking about a spring, that would be minus the spring constant times the displacement x. So we're going to go through a few detailed examples of objects that can be described as simple harmonic oscillators. We're going to start with a mass on a spring, which is the example we used before. But this time we're gonna try to make the graphics a little bit neater and more fun. And generally that'll be what today's about. We're going to be looking at how to visualize these in kind of fun ways. So we'll do a mass on a spring. We will do a floating object. So in this case, it'll be a boat that's bouncing up and down in simple harmonic motion through the force of buoyancy, which is causing that motion. We'll look at a pendulum swinging back and forth. We'll look at a piston and the gas inside the container for that piston that, through its pressure, will create simple harmonic motion. We will look at the elasticity of a material that, when you strike it, will vibrate back and forth in simple harmonic motion. We'll also look at an LC circuit, which is an inductor and a capacitor in series. And we'll see how that undergoes simple harmonic motion. And finally, we'll look at optical absorption, which can be described almost by treating the electrons kind of like masses on a spring. Each of these examples is going to have several different components. I try to get a nice picture to get a good visual in there. But we'll have a setup, and then we'll go through the solution, and then we'll go through the animation. We're going to start off nice and easy using an example we've seen before, a mass on a spring. This time we're going to do it a little bit differently. We're going to try to make the graphics a little bit nicer, since it's just a little bit more fun. So the setup for this problem is we have a mass, in this case represented by a ball, and it's attached to a spring, which you can see here, and the other end of the spring is attached to a wall, and the wall is fixed. We're going to take that mass and we're going to displace it from the equilibrium position, which we've set at 0, and we're going to call that displacement distance x. As you know from Hooke's law, the restoring force on the mass from the spring is going to be equal to minus some constant, which in this case is just the stiffness of the spring, times the amount we've displaced it by. To solve this, we need to define our constants. Then we will set up and use Mathematica's dsolve function, which will take in the force equation along with our initial conditions. And when we do that and we run that, you can see I ran it a little while ago, you get your solution equation here. We can now run the graphics for this, which here I am not going to go through in detail all of the commands here, but I'll leave this up so that you can see it, pause the video, and try to copy it on your own. But we're going to have we're going to define a few functions, one of which is going to be a particle, which in this case is going to be the ball. That's our mass. Then we're going to use a spring here, which will use a parametric plot 3D to create that spring. And then we're going to use an animation command where we show the spring and the particles. And if I run that, you can see we get a nice graphic showing our mass on a spring. And it's 3D now, so I can move it around in different directions. And if I hit play, you can see the simple harmonic motion of the mass on the spring. So in general, for these examples, I am not going to take the time to go through the animation stuff. We'll go over a little bit of the physics and why the forces follow a Hooke's law type equation, but I'll leave it for you to work out the animations. Our next example is going to be a floating object. In this case, we're just going to consider a boat that's bobbing up and down in the water. To set this up, we are going to create a boat that's floating on water. The water has a density of 1,000 kilograms per meter cubed. That's something you can just look up. The boat is displaced by some distance from its equilibrium position. Please note that I'm still calling the displacement x, but this time x is in the vertical direction. We also have the acceleration of gravity g, which is 9.8 meters per second squared, which is going to be pulling the boat back down to its equilibrium position. And the boat has a cross-sectional area, so this is the area of the bottom of the boat, which I'm going to write as 100 meters squared. Now, if I look at the buoyancy force, which in this case is going to be, we're going to be treating as the restoring force on the boat. That is going to be equal to minus a constant, in this case a group of values, which when you multiply them together gives you one big constant, times the displacement. So just like Hooke's law, it's a minus a constant times the displacement. But here, the constant, if you work out the physics and the math, is going to be minus the density of the water, rho, the Greek letter rho, times g, the acceleration of gravity, times a, the area of the bottom of the boat. And if I plug that in, I can write the equation of motion for that, the force equation. I can define all of my constants in the problem. And then I can, again, use Mathematica's dsolve function, which I will do now. And you can see you get your solution there. And if we want to animate that, here I've actually, to make this a little bit nicer and to save myself some work, I've actually put, I've stolen a picture of a boat from online. This is from the free image site Pixabay. And you can see, we run this code. I'll scroll up to the code one more time in case you want to pause and copy that code down. But you can see you get an animation of a boat bobbing up and down that looks kind of neat. For our next example, we are going to consider a pendulum. So a pendulum is a mass on either a string or a light rod, and the mass is just going to be swinging back and forth. So to set this up, we're going to consider a mass. In this case, we're looking at a pocket watch suspended from a string, which is hanging from the ceiling. The string has a length L, which I am going to define to be 1 meter in length. Gravity is going to try to pull that watch back to its equilibrium position, and it's going to do so using the acceleration of gravity, which is a constant equal to 9.8 meters per second squared. And we're going to look at that string, and we're going to say it makes an angle theta with the vertical. Now, since we are dealing with an angle here rather than a distance displacement, rather than having, since the pendulum is swinging at an angle rather than just moving back and forth in a straight line, we are going to be dealing with angular forces, which are also known as torques. So the equation for torque is given by the Greek letter tau, which is equal to the moment of inertia, which is given by the symbol I, times the angular acceleration, which is given by theta double prime, which is the second derivative of the angle with respect to time. So looking at the rate of change of the angular velocity, which is the angular acceleration. Now you'll note that even though the letters are different, if you stare at this a little bit, you can see it's very similar to our original Newton's second law, except instead of force is mass times acceleration, you get angular force, torque, is equal to moment of inertia, which is kind of like the angular version of mass, times the angular version of acceleration. So angular force equals angular mass times angular acceleration. Nobody says angular mass, but you can roughly think of moment of inertia as being that way. If you work out the equation for the torque, and you assume that the angle is small enough, you can approximate it again as being minus a constant times the displacement, although in this case it's the angular displacement, so it's a theta, not an x. And the constant is given by the mass times the acceleration of gravity times the length of the string. So it's just like Hooke's law minus a constant times the displacement. We can plug that in here to write our equation. Note, I am using the lowercase I rather than the uppercase I, which is more common in physics books. The reason why is that uppercase I is a symbol for the square root of -1 in Mathematica, so I can't use an uppercase I as my variable here. So I'm just going to stick with the lowercase I. We can plug in the equation for the moment of inertia, which you can just look up for a mass on a string. And again, we plug in our dsolve. We plug in our equation of motion, the initial conditions, hold down shift and press enter, and we get our solution. Just like before, we can do our animation. I will hold this screen up for a second in case anybody wants to pause the video. Highly recommend you try to go through and reproduce this yourself. But if we run our code, you can see we get a nice animation of a pendulum, in this case, a pocket watch swinging back and forth. For our next example, we are going to be looking at a piston. So you can, if you've ever wondered how things like combustion engines work, usually you have some piston where you have a gas that's expanding and contracting inside because of the combustion that's creating energy that turns a crank. We're going to deal with a much simpler version of a piston, so not any full combustion engine here. We're going to be dealing with just a single piston inside a cylindrical container. There is some gas inside the container so that when I put the piston inside, the pressure of the gas will suspend the piston up so it won't fall all the way to the bottom. And it'll be suspended at some equilibrium height, which I'll call L, which I will set to be 0.1 meter. That's the equilibrium height that the piston would be at if it were not displaced. We are then going to displace a distant x. In this case, again, x is going to be in the vertical direction. So x is vertical. We're not going to call it y. Again, we have some pressure, which for convenience, I'm just going to be, I'll just take that to be atmospheric pressure, which is 100,000 pascals. And the cylindrical container has some cross-sectional area A. If you work out the restoring force on the piston when it's displaced from equilibrium, that force will be the area times the pressure, or excuse me, it will be minus the area times the pressure divided by the equilibrium height, and then times the displacement. So again, we're just looking at a simple harmonic motion equation, Hooke's law, minus a constant times the displacement. We can create that equation in Mathematica. Again, we can define values for our constants. Again, we can use dsolve. We can plug our equation of motion in. We can set our initial conditions. And we can run that to get our solution. I'll just comment that out to make sure I just have the solution. That's the output. And we can set up an animation. Again, I will pause here to make sure. Oops, got a blue L here. I did a variable change, so I'm just going to change all these L's really quick to be uppercase L's so we don't get any errors here. I'd used lowercase l originally, so we're just fixing that. But we'll just go ahead and animate this now. You can see we get a nice 3D graphic of a piston using the code up here, which again, you can pause the video if you want to copy that down and reproduce it. But we can just plug in our solution and you can see that piston moving up and down in simple harmonic motion. For our next example, we are going to be looking at an elastic material and how its surface vibrates when it's been struck. So to set this up, we are going to imagine a beam of material. In this case, I think we chose copper. That's rigidly attached to a wall. The beam has a length L, which I'm going to set to be 1 meter. It's got some cross-sectional area. And when you strike the end of it, it will compress, and then it will expand and contract and expand and contract, so that the end of the surface of the material has some displacement from its equilibrium position. And the frequency of the vibration is going to be determined by its elasticity, which is determined by Young's modulus, which again we chose to consider a copper rod here, and Young's modulus is about 130 gigapascals for copper. If we look at the force equation that describes the stretching and compression of that surface, of that material, the force is again given by Hooke's law, which is just minus some constant times the displacement. In this case, the constant is equal to the area times Young's modulus divided by the length of the beam. Again, you're going to see a pattern here if you haven't already. We can write down our force equation. We can define our constants. We can use dsolve to solve the force equation by plugging in the force equation and giving some initial conditions. If we hit Shift-Enter, you can see what the solution is. We can set up an animation for that. Again, I will pause here in case anybody wants to stop the video and copy the code down and try to reproduce this on their own. And when we run this, we get an animation, a very zoomed in animation, because again, the vibration of a piece of material is going to be very small, but you get a very zoomed in animation of what the motion of that surface of the rod of that beam is going to look like after we strike it. Our next example is going to come from the electronics world. We're going to look at a simple LC circuit. If you've taken either an electronics course or a second semester physics course, you've probably done some simple circuits. In this case, we have a capacitor in series with an inductor. Now, you might be thinking this is very different from a spring equation. We're going to have to deal with voltages, not forces, but if you look at the voltage changes around the loop, you get an equation that looks like this. Using Kirchhoff's laws, you get the voltage equals the inductance times the rate of change of charge on the conductor. So that's the voltage drop across the inductor. And that has to be equal to the voltage drop across this capacitor, which is equal to -1 over the capacitance times the charge on the capacitor. Now, even if you have never taken an electronics class, even if you've never seen circuits before, you can look at this and say, ah, that's the equation for a simple harmonic oscillator. It's like the voltage is the force equals some mass, which in this case, we're going to treat the inductance of the inductor as the mass, times the second derivative of Q, which is the charge on the capacitor, second derivative of the charge with respect to time. This is just like forces, mass times acceleration. It's just that the variables are different and they mean different things. And that's going to equal minus a constant, which in this case is 1 divided by the capacitance, times the displacement. It's just like my Q in the second derivative here, and the displacement here is like, or the charge here, is like the acceleration and the displacement in a simple harmonic oscillator. So even if you know nothing about circuits, you can still solve this problem because it's the same math. So we're going to solve this equation. Again, we set up our equation, we define our constants, use Mathematica's dsolve to solve by plugging in the equation of motion, plugging in some initial conditions. I'll comment this out. We'll get our solution out. And again, I'm actually not going to animate this one because circuits just look like circuits. But I will do a plot of the charge as a function of time. And you can see it goes up and down in simple harmonic motion. For our last example, this is one that is very near and dear to my heart. We're going to be looking at the optical absorption of a nanoparticle. So nanoparticles, you can see some example solutions of them here. And when you get to the nano world, physics gets a little bit different. Some of the material properties that you're used to at a macroscopic level don't hold for the nano world. So all of these different color solutions are really just gold solutions of gold nanoparticles. So they're teeny tiny gold particles that are suspended in the liquid here. And you might say, hey, wait, that doesn't look like gold. Gold's kind of a shiny yellow color. Well, it turns out these are gold particles, but color changes because light gets absorbed in different ways for different sizes of material when you get down to the nanoscale. So as we go from left to right, you get different you get different colors based on the optical absorption. We're going to do a very simplified version of what happens when light hits a nanoparticle. And we're going to just treat it with Hooke's law. So if you have a metal nanoparticle, you've got charges on that nanoparticle. So you've got positive charges, which I am showing in red. You've got negative charges. So your positive charges are the protons. You've got negative charges, protons and the nuclei. You've got negative electrons that can be displaced and stretched away from the particle. And I am making up arbitrary units here just to get a visualization that looks nice. So don't take the numbers too seriously, but we can treat the displacement of the electrons as being some distance x. And again, we can model that with Hooke's law, assuming we have some stiffness k, that's some restoring spring constant k that's going to pull those electrons back to be on top of the positive charges. So we've done this many times. You create your equation of motion, define your constants, set up your differential equation solver, plug in your equation, plug in your initial conditions, run that to get your solution, comment that out. And again, we can just play around and get a nice visual of what that is going to look like. And you can see those negative electric charges sloshing back and forth. Now, how this affects the color just as a quick bit of trivia. So the shape and the size of the nanoparticle determines how stiff the spring is that's pulling the electrons back. If it's a stiffer spring, they're going to vibrate more frequently. They're going to have a higher frequency of vibration. And that's going to affect what frequency of light gets absorbed. So when we're looking at these different colors, all of that is just because of Hooke's law and because of the oscillatory motion that the electrons are going. So you can start to see that simple harmonic motion, all of the things that we're covering in this video series, has a real practical benefit looking at how we can design new materials with new and interesting properties. That is all for this time. Join us next time where we'll explore how the Taylor series explains why all these different systems behave very similarly and undergo simple harmonic motion. Thank you for watching, and if you liked the video, please click like, and if you would like to see more, please click subscribe.